All right, so what we're going to take a look at today is, well, I guess good news, bad news. Good news is this is the last day for all of the rules you know and need to know for this course. However, that means there's one more thing to know today. So this is about inverse derivatives, because there is a special relationship between a function and its inverse. We've seen what it looks like in graphs. We're going to take a look how that connects itself to the tangent. It's nice to see so many of you are taking calculus serious enough to come here in suits and ties. It's good. It's a good start. It's formal day today, I'm assuming, yeah? Okay. Anyways, let's have a look at these two. We're going to try and hash out what it means. This is one of those things which is very simple and very complicated. You'll see what I mean in a second. It's a real simple relationship, but it's difficult to describe the first time you look at it. So let's try that simple stuff, and we'll see if we can hash out this relationship. We're going to take a look at the derivative for a function and its inverse. So I'm just picking something fairly gentle, like a parabola and the square root. So what's the derivative for x squared? All right. And for the square root? Okay, so that means I have a couple derivatives now. We can take a look at what will happen at these points. So if I'm at the point 2, 4, the derivative at 2 is going to be 2 times 2, which is 4, while the inverse at 4 would have a derivative of 1/4. Now some of you are going to jump to some conclusions about this right away, because I told you there was a relationship. That's good, I guess, if you're thinking that way, but maybe it seems so obvious that you wouldn't want to say it. So let's try it again and see if it keeps happening. Let's take a look at the points 3, 9 and 9, 3. So the derivative at 3 would be 2 times 3, so a 6. Now, if you've made a wild guess about what's happening, maybe you can tell me the answer before you have to calculate the next one. Okay, well, let's see what happens. This time I'm going to look on that inverse derivative, and I'm going to do that at 9 and see what I get. So, what is the simple, and this is the part where I said there's something very simple happening which is difficult to describe. So what's the simple thing that you see? Yeah.
The derivative of the inverse function is 1 over the derivative of the...
Yeah, so, sorry? Reciprocal, good. That's the word we were looking for. Now, the reason it's a little trickier than it seems is we're not dealing with the same points. If you take a look, on the function, I'm at 2, 4. On the inverse, I'm at 4, 2. It's not happening at the same place. However, it is the reciprocal. What's special about 2, 4 and 4, 2? They're the opposites, yes. But why is this important for the inverse? So the x and y have switched, like the transformation that we looked at when we did the graphs. So the relationship, that point, if 2, 4 is on the function, its inverse will have the point 4, 2. Same thing, if 3, 9 is on the function, that means the inverse must have the point 9, 3. Yes? Does it have to be?
Does it have to be squares or square root? 2 squares, 4, 3 squares.
Well, I picked nice numbers so that we would end up with nice derivatives. No, I mean, I could pick any number I want, but if I pick a number like 7, then I'm going to have square root 7 somewhere. It just works out nicer this way. Try and keep it as simple, right? So this is what it formally looks like, and this is where, like I say, right now you might be saying, oh, okay, well, I get it. It's a reciprocal, and you got to go from one graph to the other, so you flip the x and y, but that's what the math looks like. Yes, horrible and frightening, I know. But basically, if we take a look at what this is saying, is you need to go, if you want the inverse derivative, you need to go to that flipped point. So you don't get to just stick in x, you have to go to the flipped version. For example, this is x and y, so when I go to the inverse, then it changes. This becomes x and y. They switch. So that's what that first part is saying. You can't just take it at face value. You have to go to the inverse, and then you're going to find the derivative there and take its reciprocal. So we're going to practice this a few times because this is not a very practical definition. One of them that I like better is this. This one I think is easier to understand because the inverse value at x is the same thing as the function at y. So that way we can cut down on all of the notation. It's not as horrifying and frightening as the one on the left that appears in your textbook. Instead, I'm just saying don't use the inverse at x. We're going to use the function at y. All right? So up here, what we looked at was, as soon as it stops moving, there we go. For example, the function at x is the same as the inverse at x is the same as the function at y. The inverse at x is the same as the function at y. This way we can keep talking about the function and we don't have to use the inverse in that part of it anyways. So enough of that. Let's try and see what happens. If I have a function where f of 3 is 5 and the derivative of 3 is -2, what can we say about the inverse? Right? We don't actually need to know what the inverse function is, but we can say something about its derivative. So can we make that bridge? -1/2, I agree. Where? So this is the inverse derivative of something will be equal to -1/2. And we'll talk about why that is in a second, but good, that's the first part. Yep. Can you give me the number that goes in that box? Which is? This is what okay, so again, this happens every year when we do this. This is a simple relationship. It is a reciprocal. That is all it is. So Eddie saw the -2 and he said, okay, that's a -1/2. It's a reciprocal. That part is simple. Here's the confusing part. Where does it happen? What point does this represent? Can somebody tell me what point this represents? Don't think any further ahead than where is this point? 3,5. So this is where I'm at on the function. Where's its partner for the inverse? 5,3. So on the inverse graph, this is where I am. This is the point that has that simple relationship. The value I'm looking for is the 5. Okay? So the inverse at 5 is -1/2. I start on the function, I use its derivative, then I jump over to the inverse and take its reciprocal. Those are the connections, right? So we'll try this again. If this time the inverse has a value of 2, or at 2 has a value of 1, the inverse derivative at 2 equals 5, what could you say about the function? Okay, so what is the let's break it down in simplest terms that we know. What is the simple relationship? I'm not looking for the whole description. Loosely, there is a very simple relationship between a function and its inverse regarding its derivative. What is that? The reciprocal is the relationship between the function and its inverse for the derivative. So we remember that. It's got to have something to do with the reciprocal. Why don't we start there? We know that the derivative somewhere is going to be equal to 1/5. That's the simple part, which says it's the reciprocal. Now the tough part is to remember there's a connection between the function and the inverse, and that's where it counts. Where is the point I'm starting out with? What are the coordinates of the starting point? 2, 1 is where I start. Where will I be when I end up on the function? So that means I will end up at 1, 2. So where is the derivative equal to 1/5? At 1. Good. Okay, so the simple thing, it's confusing, I know. It takes a bit of practice, but the simple part is it is merely the reciprocal. However, it is not where you see it at x equals 2 here in this example. You have to go from that function and flip across to the inverse where the point becomes 1, 2. That's why it's at 1. Okay, so I would like you to have a little bit of a discussion with your neighbor here and see if you can fill in this table. You should be able to find all the missing pieces given what we just talked about for inverse functions, functions and their derivatives, and that relationship. So see if you can fill in those missing boxes. So this table is supposed to illustrate that connection to you again. If you start with the 0.71, that means the only thing you know about the inverse is it's going to have that 0.17. But then now we can take it a step further and say that if you know the derivative is 8 at the point on the function, when I jump over to the inverse at 1,7, it'll be 1 over 8. It's reciprocal. And I should be able to go both ways. So when I go to the next part of the table, if I'm on the inverse and I have 3, 6, that means I'm going to have 6, 3 on the function and 1/2, the reciprocal, for its derivative. And I can keep trying to piece these things together here. If it's negative 3, then I would know it's negative 1/3. That's the simple relationship. The tough part is remembering where it happens. If this is at negative 5, 2, then it must be connected at 2, negative 5. This is where we would see it. So this will be at 4, negative 1, and then this will be at negative 1 over 7 because that's the reciprocal. So now what I'm going to have you do is actually try it on a couple of functions here. So x 1/4 x cubed plus x minus 1 doesn't seem like it's all that difficult in terms of what a function might look like. However, its inverse, I can show you a picture of it. Q plus y. And of course I forgot a y in here. So here's the inverse function. It might have a nice simple way of describing itself, but think about how you would solve that. It looks like it'd be fairly difficult to pull apart all the x's and y's. First we switch x and y, then we solve for y. I think that'd be a fairly difficult thing to solve for y here, unless you know something about solving cubic equations, of course. So the point is we don't actually have to find its inverse. We can just say, if we use the function and this relationship, we can figure out what the derivative is of the inverse by going backwards. So if I'm talking about the inverse derivative at 3, that value is on the inverse. So when I march back to the function, what do you know about it? If I march back to x cubed, 1/4 x cubed plus x minus 1, where will I find 3? It's the y coordinate. Here it's the x. So that means it's going to become the y coordinate here. So I started on the inverse graph, and I know that x equals 3. That means I'm talking about the y coordinate, and now I can figure out where x was. So I'll let you work through this and figure out what the value of x is, and then see if you can go the step further of that has a simple derivative. Can you find its derivative and then use it to figure out where the inverse was? So I'll pull up the TI-83. And I'm going to end up doing this for 1/4 x cubed plus x, take away 1. And I'll put down y equals 3. And then I'll use the intersection method of my TI-83 to figure out what's my possible answer. I can see 1 exists there. So I'll calculate where they cross. Looks like about 2. And it tells me that it is in fact 2. So if x equals 2, then the place that I'm at is 2, 3. And the derivative is 3/4 x squared plus 1. So the derivative at 2 is 3/4 times 4 plus 1. So 3 plus 1, which is 4. So I know that at 2, 3, the derivative's 4. So again, the simple relationship is I know that the inverse is going to have a derivative of 1/4. Where will it happen? If this is where it is on the function, it will happen at 3, 2, which is what I'm looking for. So in this case, I find that the inverse has a derivative at 3 of 1/4. So the next question should be even more familiar to you because we've done this one so many times, trying to figure out an exact value for trig. All I'll remind you to get started is, if I would like to know the inverse derivative at a half, this is the x coordinate on the inverse. What does that tell you about when you jump back over to the function? What will you know about your function? If the x value is a half in the inverse, you have a starting point. People running away trying to calculate this, or can I at least have... Huh? The question was, if you have this clue that x is a half in your inverse, what do you have to take from that just to get... Good. Y is a half. Thank you for, oops, not making me look like I had taught you nothing. Okay. Even though that may in fact be the case. So there's a starting point for those of you who are still working out this connection. Okay, so the two places that we were talking about, the first one is if I know that pi over 3.5 has a derivative of negative root 3 over 2, then when I jump to the inverse, I will be at 1/2 pi over 3. That's the new location. That's the point I've written in black. And the derivative there will be the reciprocal. So no longer root 3 over 2, but 2 over root 3. Okay. Question? Yes. Sorry, just a second. The tablet's run away from me. The first question. So further up. Okay, let me just... x cubed? Yes. Yes? can I put in, okay, let's have a look. Could do, let's have a peek. Oops, sorry, it was this one that we were looking at. So I need to zoom my window out, is that what you're telling me? Let's try negative 20 to 20. Where is the second solution? Negative 1? Well, if I put in negative 1, unfortunately I don't think that is going to give me a value of 3. I can see here in the graph, if I put in negative 1, it's going to be down here. So anyways, I believe according to this picture, it should show you that there is in fact only one answer there. Okay, so now that you know a little bit about the way an inverse is connected, we can use that relationship and we can find the inverse trig derivatives. And that is in fact the last thing that we will do for rules, the last functions we haven't talked about. So for example, if I wanted to show you that the inverse derivative for the tangent, I could use this fact. So I'm going to say that we'll pretend that I actually have two functions here. And I'm going to call it, just to get rid of all those symbols, let's say g of x is the inverse or the arctangent. So the relationship that we've just talked about, the derivative of g is 1 over the derivative of f if I find it here. So this is that definition we started with. And if I try to work this through, I can just substitute the derivative at the arc tangent of x, and this is going to be oops, sorry. This one here is actually, I kind of skipped a step, so I'll put it back in. This derivative, just so you can see where I skipped, that would be secant squared of x, the derivative for tangent. So this would be secant squared at arctan of x. And I can use one of our Pythagorean identities. So sine squared x plus cos squared x is 1. So if I divide everybody by secant, or sorry, by cosine, this will be tangent squared x plus 1 is secant squared x. So I can replace this secant squared of arctan. Instead of working with that mess, what I can do is say that's the same thing as 1 over tangent squared of arctan of x plus 1. So that was the trig identity. And this is a function and its inverse, the tangent of the arctangent. So all that's going to come out of there is just what you start with, so x. So the derivative of the arctangent is 1 over x squared plus 1. Now, the other functions, I've got a little table summary here for you to work with. They have a fairly good connection that you should know to help you remember some of these. It's not practical that you derive it when it's time for you to write your AP exam, but if you may or may not notice the way I've arranged this, the graphs, the derivatives on the left-hand side are the positives. The derivatives on the right-hand side are identical with the fact that they have a negative in front. So although there are 6 things there, there's really only 3. The others are just the negative version of it. Now, the connections, this one is for the arc sine. Arc cosine is the negative. If you're talking about arc tangent, you'd be dealing with arc cotangent for the negative. And with arc secant, arc cosecant is the negative that are connected together. And if we had to talk about stress levels, and oh my God, now we've hit all the rules from calculus, and there's a lot to remember. If there were 100 questions, I would say that 70 of them live on this row here. And I would say, well, it's probably more like 80 of them live on this row here. Then I would say 19 of them live on this row here, and maybe one of them lives there. It's not very often. It doesn't mean you're off the hook, but it's not very often that the worst of them is actually chosen for your knowledge. So that's the only caution I will give you is at the moment, that would be my priority of learning them. But you are, in fact, still responsible for knowing those, and they are on the inside cover of your book. All of those rules that we've summarized, I've attached them here. So these are our rules for calculus. And I just added the inverse ones to it now as well. So we'll just practice and see how this works if we were to try taking some inverse derivatives. Okay. So for arc sine of 2x, the pattern for sine is going to be, I like to think about it, this is the way your textbook writes it. I don't like to think of it this way because they're just adding chain rule for you. I just like to think of the simplest form. And this is the simplest form for just the arc sine of x, and this one is the arc cosine of x. Because then when I come across something like this, all I'm thinking of is it's going to be 1 over root 1 minus 2x squared times the derivative of the inside, which is 2. So this would be 2 over root 1 minus 4x squared. Okay. Again, with tangent, the simplest form that you would expect to see it, tangent of x, just looks like this. If you have more than an x, you just apply the chain rule. That way you don't have to think too much more than what the textbook has done. I don't think they're doing you a favor by adding in all that extra notation. That's what I'm trying to say here. So for tangent, I would have 1 over 1 plus that 3x all squared times the derivative of the inside, which is 3. So this will be 3 over 1 plus 9x squared. Okay, so have a go at the last two there, and then I'll try to catch up to you. Okay, so for this one, the simple pattern again is just 1 over 1 minus whatever you've got squared. What I have is a square root, so I need to use the chain rule. And in this case, the chain rule would give me a derivative for 1 over 2 root x that I'd have to add to the problem. So after a bit of simplifying, I got to 1 over 2 root x minus x squared. So here, if I've got the arc secant of e to the 2x, e to the 2x is what goes into this pattern here, and then I'm multiplying it by its derivative. So I'm going to just follow the pattern, which says it'll be 1 over the absolute value of e to the 2x times the square root of e to the 2x squared minus 1. And this has to be multiplied by the chain rule here for e to the 2x. So that's what I would get after all of that. I would have to multiply in e to the 2x times 2. I'll do a little simplifying here so you can see what would happen. And does anybody think they could simplify this anymore? Yeah, the absolute value is not necessary because the exponential graph is always positive. So because the absolute value is not necessary, those e to the 2x's would factor out. And I would just end up with 2 over root e to the 4x minus 1. So again, this is probably the most obscure topic in the fact that those derivatives aren't the prettiest ones to deal with. It is a reality that you may be asked to demonstrate that knowledge, so you're not off the hook, but it is fairly obscure as far as how often that comes up as a knowledge thing. So don't sweat it right now at this moment, but we need to practice it a little bit more along the way to May. So here is one where I would like you to try simplifying it. So take its derivative and try to simplify it. You'll find you get a much simpler answer if you use a little bit of algebra here. So first find its derivative, then try its simplified version. Okay, so let me see what I can simplify out of this. Okay, so I definitely see a common denominator here, and that's what I'm going to work on combining. If I was to multiply in a root 1 minus x squared, then I could tidy it up. So I'll have, let's see here, 1 plus 1 minus x squared plus negative x squared. And on the bottom, so I'll end up with 2 minus 2x squared over root 1 minus x squared. It's getting exciting. Look at how tidy this is getting. All right, so somebody at that textbook publisher must have been really happy with themselves for coming up with an example like that, which tidies up so neatly. But anyways, that again is just an indication of the expectation your textbook has on your algebra skills, not necessarily what you'd expected from your AP exam.